All right, another example. So here we have a pulley system with two masses. What we're supposed to figure out is the acceleration of this system. Now we're going to have to assume that we've already broken the static friction and that we're moving, and that this is the kinetic friction. In order to do something like this, we're going to have to make a free body diagram of both boxes. So let's start off with mass 1. Mass 1 is going to have a normal force because it's resting on a table. It's going to have gravity. It also has tension pulling it to the right and friction pulling back the other way. Mass 2, on the other hand, only has two forces. It's got its weight and tension. Like many pulley problems, the easiest way to find the acceleration is consider this to be one object. In other words, we're going to call both objects together the system, which means that our tension are internal forces and we can ignore them. So we have to think about this. The direction of motion for this mass here, mass 1, is going to be to the right, and for mass 2 it's going to be down. So in both cases we're going to consider that the positive direction of motion. Pulleys can kind of mess with you a little bit because they change the direction of motion, but let's face it, if M2 goes down, M1 has to go to the right. So in a sense they're the same direction. And it sounds kind of strange, but in this case it works out that way. So what's making this thing go? Well, the answer is the weight. The weight of the one hanging off the pulley is what's driving this thing. So when I say the net force here equals the mass of the system times A, I'm going to make some substitutions. The force that's driving it forward is the weight of the second box. The force pulling against it, since we get to consider tension and internal force that's going to cancel out, the only thing that's really pulling against it is the force of friction. And that's going to equal the mass of the system, which is both of the masses combined, times the acceleration. Now let's make some substitutions. The friction force is equal to mu times the normal force. The normal force, because there's going to be no acceleration in the vertical direction, is going to be equal to m1g. So if I combine these two equations together with a substitution, I get that the friction force equals mu times m1g. Now I can substitute that in over here, and I'm going to get that m2g minus mu m1g equals m1 plus m2 times acceleration. And if I divide both sides by the system mass, I'm going to get that the acceleration equals m2g minus mu m1g all over m1 plus m2. Okay, now let's play with this a little bit. I'm going to extend this up. And one thing that I'm seeing here is that I can factor g out of the top, and I'm going to do something like this, and I'm going to get that the acceleration is equal to m2 minus mu m1 and g all over m1 plus m2. And one thing I kind of want to point out to you is that if you kind of draw a line kind of around this part of it, all you see is a bunch of masses and this coefficient of friction put in here. So the units of that whole thing is nothing because I'm dividing mass by mass. And what I'm going to see is that I'm going to get some number times g. Okay, g is an acceleration, a is an acceleration. Makes perfect sense to me. So let's plug in the numbers and see what we get. m2 is 2 kilograms. Mu is 0.2. And we've got 5 kilograms. And the total mass is going to be 5 kilograms plus 2 kilograms. Let's not forget 9.8 meters per second squared over here. And when the dust all settles, here we're going to have 2 times 0.2 times 5, which is 1. 2 minus 1 is 1 over 7. I'm basically going to get 1/7 of g, which is 9.8 meters per second squared, and that's going to come out to 1.4 meters per second squared. Now, an add-on to this type of problem very often is, so what's the force of tension? Okay, now in order to do that, we're going to have to go back up to our free body diagram and pick one of those that has tension in it. I like this one. This one only has two forces in it. And what we can do then is create an equation from that. And if you know what, I'm going to transfer that down below and then redraw it, and we're going to make an equation. So we're going to have our free body diagram. Okay, so what I'm going to get is that the net force equals m, in this case m2, times a, because this is the only mass in this free body diagram. And my force that is in the direction of motion is m2g. My force opposing it is t, and I get m2a. Now if I solve this for t is going to be equal to m2g minus m2a. And we can even factor that and make it m2g minus a. We put in the numbers. M2 was 2 kilograms. And we've got 9.8 meters per second squared. And the acceleration that we got before was 1.4 meters per second squared. And when the dust settles, my tension is equal to 17 newtons. Let's see if that makes sense. Okay, the weight of this box, m2g, is 2 times 9.8, which I think is 19.6 newtons. So we've got a weight of 19.6 newtons and a tension of 17 newtons. 19.6 is bigger than 17. This thing ought to accelerate downward, and certainly that's what it's doing.